Hello, Sandon. Good morning.
Good morning, Dinesh. How are you? All good?
Yeah, Sandon. Good. How about you?
It's going well. Actually, I woke up late today. I slept very late, so I just woke up.
Oh, okay.
So, and I just had breakfast, and so I will be just starting it maybe probably in a minute or so. If you have anything to discuss, we can do that.
Okay. I woke up early today, actually.
No, I was awake till 6 o'clock.
Oh, God.
Then I slept. So I had just a nap of 3 hours or so.
Yeah. I know the pain as a night shift guy.
Okay, okay. I think there are two people now. Let's wait for 2 more minutes. Okay. Meanwhile, what I'll do is so I'll use the same data set which we had last time.
Uh, the diabetics.
No, not
Oh,
those.
okay. The
The for the linear regression one, the
okay.
experience versus salary one. Okay, I'll import that. I've already uploaded that. Previously, I forgot to upload a copy. I did that today.
Okay.
So you might see that in a recording probably for August 2 or August 3. You can just check out. I mean,
Okay.
I've uploaded it today itself, so you might see that file there. This file, salary data.csv. Okay. Okay. So this file has around 30 samples and two
Two
columns.
features. Okay.
And let's look at the top two rows. So these are the top two rows. You can see we have years of experience and salary. So the objective is to predict you can say the salary from this years of experience. Okay. All right. So this is our objective. So let's just plot the data. Even before plotting, let me split it and then I'll plot the training set. So I've already imported, I believe, Matplotlib. Yeah, I've already done that. So let's just plot it. So you can say, before that, let's split it. So I'll go to model selection and you can import train test split. To this train test split, you can provide the data, which is in X and Y, or in my case, this is there in DF of this years of experience. Okay, and your outcome is in the salary.
We can also give the column numbers.
You can also give column numbers. You can do it like this. You can say DF of DF dot columns of 0. That is easier way to do it. You can also do DF of DF dot columns of 1 here. So that can also be done. Okay. In case if you want to do that, I mean, this is you can do that also. Okay. Now there is one issue. I just want you to see here carefully. So if you look at this DF of years of experience, what do you think the shape of this will be? Anybody? So the data frame has 30 samples. Okay, I'm printing the shape of one particular column. So what do you think the shape would be?
30 cross 1.
It will be 30 comma, not 30 comma 1. Okay, that is the catch. Okay, so if you remember, when you're passing your input and output, right, to the fit function, what is expected for your input? The shape of the input should be the number of samples, comma, number of features. So for input, the shape has to be the number of samples, comma, number of features, which is not the case here, by the way. Okay, so I'm going to reshape this input. For output, it can be just number of samples. Okay, for output, it can be number of samples, comma. Okay, so for output, it is allowed. Okay, however, for input, it is not allowed. Okay, for input, it has to be number of samples, comma, number of features. So that's why I'm going to reshape this very first column. So let's reshape this. So first get the NumPy array. So this is how you get the array into NumPy values. And you can then reshape a NumPy array by simply saying, okay, put everything in single column. So this is how it keeps it in a single column. If you check the shape of it, this is 30,1 now. So I'm going to pass this instead. I'm going to pass this instead. Okay. And for this DS salary, you can keep it as it is. But if I ask you, after reshaping, can you tell me what is the type of it? After reshaping, what is the type? Do you think it's a data frame or it's a NumPy array?
NumPy array.
It's a NumPy array, right? So I would advise you that because your input is a NumPy array, your output should also be a NumPy array. So you can simply type dot values here. Okay. All right. You don't have to reshape it, but you can simply say dot values so that it gets converted to a NumPy array. Even if you give it as it is, it will still work. Okay. But it is, I mean, just for the clarity's sake, you should know that, okay, if input is NumPy, output should also be a NumPy array. Why to have like different, you can say data types in the inputs and the outputs. Okay. All right. So we have to specify the size of the test, how much data we should give here. Let's say 30% and a random state to ensure that you and I get the same results. Let's say random state is 1, 2, 3. Okay. You can give any number. It has to be an integer though. Okay. So this will give us your xtrain, xtest, ytrain, and ytest. Okay. So now that I have split my data, what I'm going to do is I'm going to plot it, the training set. So you can plot the training set using the scatter plot. So my training data is in xtrain. My output is in ytrain. Okay. Let me label it as well. So my x-axis is my years of experience. You can say this is your feature x1, and your y-axis is your salary, the output that you're trying to predict. Okay. And let's give a title also that predict salary from experience. Okay. So this is how the data looks like. So if you just look at it, can you tell me which model seems reasonable here? If you talk about the relationship between the input and the output, which type of relationship can be observed?
Linear.
Linear, right? So a linear regression function will do well here. So I'm going to fit a linear regression function. We have seen this before. You can treat it like a quick recap of what we discussed. Okay, so go to sklearn linear model, import linear regression, and let's just run this. So import the linear regression model. Please note that linear regression does not have any hyperparameters. This linear regression function does not have any hyperparameters. Okay. So I'm going to fit to my data. Okay. Tell me this. If you have one feature, is there a need to normalize or standardize?
No.
No. So since we have one feature, see, we are doing simple linear regression. You can also call it univariate regression. Okay. You can also call it univariate regression. So univariate regression, when you do it with linear regression, it has a special name. It is also called a simple linear regression. Okay. So if you do it with one feature, there is no need to normalize. Okay. I'll just make a point here. Okay. No need to scale your data if you have one feature. Okay. Even if you do, it will not have any harm. Okay. It will still not have any harm. Okay. If you have one feature. Okay. So I'm going to fit it. So my input data, as you would know, is in xtrain. My output is in ytrain. Okay. So the model is fit. Now let us see the slope and the intercept term. So the slope is present in your this coefficient. So this is your m. Okay, this is your m. Let's call it theta1. Okay, let's call it theta1. Okay, because you can see it's an array, right? So I'm going to take the value of this array, which is in 0. Okay, and I'm going to assign it to theta1. All right. Similarly, so this is your theta1, by the way. Okay. Similarly, I will find the intercept term, which is your model dot intercept. Now this is your C term, theta naught. Okay. And you can see it's a single value. It's not in an array. So I can directly assign theta 0 to this, and this is theta 0. Okay. So how do I make a line? What's the equation of the function?
Theta 1 m plus theta 1 x plus theta 0.
Correct. So I'm going to do that. Let's see. So if you want to plot, you can simply say plt dot plot. And you can simply say my data is in xtrain, and okay, my data is in xtrain, and what I'm going to do now is, okay, okay, before I do this, I want to do something to this data, okay, or rather it is fine, I'll do it later also, okay, and the output would be this theta 0 plus theta 1 x1. Theta 1 into this xtrain. So this is your, you can say mx plus c, or theta 0 plus theta 1 times x1. Okay, that's how the equation of the line is, right? So this is the line that you get. You can see this is, I mean, the best line that you can get as per the sum of the distances which are being minimized here. Okay. Now I'm going to show you that the thetas that you have obtained through this function, they are the same as through the process that we have studied in the class. Okay, so I'm going to show you, if you do it from scratch, then you will get the same thetas, so that you can verify what you have learned is what this function is doing. Okay, so do you remember in the univariate solution, what were the values of m and c? Anybody who remembers what was the value of theta 1? The formula for theta 1. It was covariance divided by
Of xy divided by variance of x.
variance of x. Okay, variance of this feature. Okay, I'm going to compute this from scratch. So I'm going to compute the numerator first. Okay, I'm going to compute the numerator first. All right, which is your covariance, by the way, which is this covariance. Does anyone remember the formula for covariance? This is 1 divided by n. Okay, if n are the number of samples,
X
you have the summation of
x xi minus
let me call it, say, x1i minus x1 bar. Okay, let's say the mean of x1. All right, into
y.
y, you can say yi minus y bar, or y dot mean. This was the formula, right? I hope everyone remembers. Do you guys remember this?
Yes.
The sum is on I, by the way. Okay, the sum is on I. Okay, I mean, these, you are going to multiply these individual elements and then you are going to sum it up. Okay, so I'm going to do this, see this carefully. I'm computing the numerator first. Okay, see this carefully. I will show you there are functions for computing covariance also, but let's do it from scratch so that you can follow what is happening. Okay, so let's compute this portion first, x1i minus x1 dot mean. So the data that I'm using is in xtrain. So that would be xtrain minus xtrain dot mean. So depending on how many samples are in xtrain, what it will do is it will subtract the mean from every entry and will print it for you. Can you see that? It subtracts the mean from every entry and prints it for you. Okay. Now, same thing, I can actually do it for yi minus y mean. Let's look at this. So I can say my output is in ytrain. I can say ytrain minus y dot mean, and it will print, sorry, it's ytrain here, my bad. And it prints all those 21 values. Okay. Now, can you see that the shape is different for both of them? Like one is a column vector and another one is a row vector. Look at this shape. This is 21 comma. And what is the shape of this? Any guesses?
1 comma
21 comma 1. Okay. So you need to, ensure that the shapes are the same. So to ensure the shapes are the same, I'm just going to say, okay, ytrain is equal to ytrain dot reshape, comma minus 1 comma 1. Okay. So that way you will have the shape of ytrain. I'll print the shape of ytrain also. So it becomes 21 comma 1. Okay. After this. And now if you do this, okay, it will become 21 comma 1. So they have the equal shapes now. So this is how it looks like. Okay. Now, can somebody tell me what should I do? Should I multiply this 3.18 with this number 40380? Yes or no?
Yes.
Then I should multiply this number 0.88 with this number 7931.
Yes.
You can add them up. Keep on doing this till you get each and every element's multiplication. Okay. So if you want to do element-wise multiplication, you can simply multiply the two terms. Okay. You can simply multiply these two terms. This will do element-wise multiplication for you. Okay. Please note that this is element-wise multiplication. It will not do the sum. It will just do element-wise multiplication. Okay. I hope the steps are clear. So you can stop me if I'm going too fast. Don't hesitate. So this is the element-wise multiplication that every element of what we say is x train minus this is getting multiplied with this. Okay. Now I have to sum it up, right? You can see that all the values have to be summed up. So I'm going to sum it up. So it's a NumPy array that you get in the result. So let me just do it in the next step. Okay. So I'm going to now sum it up. Okay. So I'm going to sum this up. So you can simply say sum of this and it will sum it up for you. Okay. All right. Let me just comment this part out. So it sums it up. Okay. Sorry. There's a problem here. My brackets are not. Okay. Just a second. No. This is not creating a problem. I'm just creating a problem right now. Just give me a sec. X train minus X train. What mean if I multiply this? Are my brackets correct? No, this one is not. No, I need one more bracket. And maybe I need one more bracket here also. Just a second. Yep, this is fine. Okay, so I get the sample. Okay, brackets were missing. Okay, so this is like one particular vector. This is another particular vector. You are multiplying them and then you are summing it up. Okay, so you just summed it up. And if I divide it by 1 by n, do you think I will get covariance? If I divide by 1 by n, do you think I'll get covariance? Yes or no? And what is n? N is nothing but x train dot shape of 1, the number of samples. See, x train dot shape of 1 is nothing but the number of samples, shape of 0, my bad. 21. Okay. So this is what numerator comes out to be. This is your numerator. Okay. Let's save it in numerator. Let's call it numerator. You can also call it covariance if you want. Okay. Let's call it covariance. Okay. So this is your covariance. I'm going to print this covariance. So this is your covariance. Okay. All right. So now that you have your covariance, I'm going to show you there is a function also that you can use. So in NumPy, there is this covariance that you can use. So you can compute it for X train and Y train. But please note that you have to pass a function which is called as pass an argument called as DDOF. And you have to say this is 0. Okay. My bad. Okay. It computes it the axis wise. Just a second. I think you need to do that like this. Axis is equal to 1 or something like that. No, just a second. Okay. Let me just check. How do you pass it? Okay. 1 second. It is actually doing it for every pairwise. Okay. I get it now. Okay. What is it that I have to do? Here you have to reshape this. Okay. It has to be a row vector. Okay. Not a column vector. You have to reshape it. So it has to be like this. Okay. 1 comma minus 1. This particular method requires you to pass a row vector essentially. Okay. Can you see that? Look at just a second. Look at these values. Okay. Look at these values. Okay, what is this returning you? This is telling you it's giving you a 2 cross 2 matrix. So this is actually the variance of your X train. This is the variance of Y train. And these are the values which are the covariance of X1 and Y. Is this part clear? What are these values indicating?
Yes.
It's a 2 cross 2 matrix, right? Okay, this is like this. What this method returns is, it returns a 2 cross 2 matrix for you. This is a 2 cross 2 matrix. And what this 2 cross 2 matrix contains, okay, so the first value is covariance. You can say it's the variance of X1 with X1. And what is this? I mean, if you call it covariance of x1 with x1, can I say this is the variance of x1? Yes or no? The next value is covariance of x1 with y. Okay. All right. And the next value here is covariance of y with x1. Okay. And the next value here is covariance of y with y. Okay. This is what it computes for you. Yeah, this is what it computes for you. Now, can somebody tell me what can I interpret covariance of x1 as? What can I interpret it as? Can you please tell?
Variance of x.
Variance of x1. So you can interpret this as variance of your x1, okay, comma this covariance of x1 comma y, okay, and the next value is your covariance of y with x1, and the last value is variance of y. Now, please note this. Please note this, that covariance is a symmetric metric. Okay, if you compute covariance of AB, it is the same as covariance of B comma A. You can reason why, right? So if I multiply this thing with this, don't you think you'll get the same result? If I make it symmetric, right, I'll get the same result, right? Think of doing AB and B comma A. This is like computing distance between two samples. Okay, if you do it between AB and then B and A, it will give you the same result. Okay, that's why you are seeing these two values are the same. Can you confirm this value and this value is the same or not? Can you confirm this value and the other value is the same or not? Yes or no? Okay, so this is how you can compute covariance directly also. Okay, I mean, if you want to just print this, I'm going to print this particular value. Okay, let's see this carefully. So out of this 2, 2 array, which value I need? 0, 1 or 1, 0?
0, 1.
You can print both of them, 0, 1 or 1, 0. You can see exactly the same thing that we got. Okay, you can see exactly the same thing that we got. Okay, so this is to tell you, I mean, how you can compute covariance, the numerator. Let's see the denominator. You can actually see we have computed the denominator also, right?
Yes.
Denominator is here. Yeah, this is the denominator. By the way, there is this function variance also that you can use. That so if you want to compute the variance for x1, which is the x train, provide this DDOF is equal to 0. Degree of freedom is equal to 0, and you can see this is the degree of freedom with this particular variance. This is the number. Okay. Now, if I'm going to divide these two entries, what will I get? If I divide these two entries, what do I get?
Theta 1.
The theta 1. Okay, so you will see I'll get theta 1. Just confirm if this is the theta 1 that you get. 9602. Okay, do you see that? Yes or no? Are you convinced now? I'll just copy this and paste it below. Are you convinced both are the same values?
Yes.
It's just one, it has rounded off 955 to 96. Okay, so the formula that we know is actually correct. Okay, that way. Let's try to get C. Okay, so this is your theta 1. Let's try to get C. See, I'm telling you all these formulas because when you are doing the computations from scratch, right, these functions you can use over and over for different tasks. So you'll be using them when you do data science. Okay, so let's do your theta 0. What's the formula for theta 0 if anybody remembers?
Y mean minus theta 1 into x mean.
Y mean minus theta 1 into x mean. Okay. Yeah, this is the formula for this. All right. So let's compute this. So y train contains my output. Y train dot mean would be y bar minus theta 1 I just computed, which is this value. So I'll just save it as theta, or I already have computed theta 1, right, previously.
Yes.
So we do the same thing, minus x train dot mean. Okay. Confirm this. Okay, this is the value that you see above. This is theta 0, by the way. This is your theta 0. Let's see this. It is 25235. Do you see that? I'll just paste it below so you can compare. Okay. So what you know is actually correct. This is what the function computes. Okay. But let me tell you, this is not what the function computes. It uses a different formula. Okay. And both the formulas are equivalent. What you just computed, right? I told you the formula which it uses is called as the closed form solution. The formula which this method uses is called as a closed form solution. Does anyone remember the closed form solution? X transpose, okay, into X whole inverse
X transpose.
into X transpose into Y. Okay. This is the formula that you can use to compute the thetas. So basically, this will give you two thetas, theta 0 and theta 1. Okay, it will give you two thetas, theta 0 and theta 1. This is the closed form solution. This solution and this solution that we got, right, for theta 0 and theta 1, they are equivalent. They are the same thing. You will see that now. You will see that now. Okay, both the solutions are equivalent. Okay, let's try to get theta 0 and theta 1 in one shot instead of doing C and M separately, theta 0 and theta 1 separately. So this solution and the previous solution that we showed, they both are equivalent. Okay. So this is the function which your linear regression uses, by the way. Okay. Let's see this. Okay. Now, I'll be needing some functions that can multiply matrices. Okay. So my explain is this. Okay. This 21, 1. If I want to take the transpose of it, you can simply say dot T. This will take the transpose of it. Okay. If you want to take the transpose of a NumPy matrix, you can simply say dot T and it takes the transpose. Okay. My question is this. Do you remember we should do something to this X to make it capital X? What we should do? I told you there is add a column
With all values as 1.
ones. That is what we have to add. So I'm going to add a column of ones to this. That is important. Okay. So let's first use this NumPy function, which is called as ones, and it can generate a column of ones for you. How many ones do we want? We want it to be equal to the number of samples. And how many number of samples are there? In xtrain.0. So this will create, sorry.
Still not shape.
Oh, sorry. I missed one. Yeah, my bad. Okay. So this will create 21 ones for you. Okay. And now I have to concatenate it. So let me just reshape it, because if you see the shape, it is 21 comma right now. Okay. So I'm going to reshape it into this matrix of, you can say, this one column vector. Okay. And now I'm going to append this column in front of this xtrain. Okay. So for that, what you can do is you can simply say numpy.concatenate. Okay, you are going to concatenate two things. This is one thing and the other one is xtrain. Okay, these are the two things that you have to concatenate along the axis of the rows. So this has to be merged row wise, right? It is not supposed to be one after the other. It is supposed to be side to side. Okay, so if you do this, sorry, it has to be axis one, my bad. Column wise. Okay, column wise concatenation. So this concatenates it column wise. Okay, and this is what we need. So this is your X, by the way. Let's say small x. Okay. So this is your X. Okay. If you look at the shape now, this is going to be 21, 2. Okay. I'll just print X and the shape is going to be 21, 2. Okay. So I want to take the transpose of this. So this is the transpose. Okay. This is the transpose, you can see. Okay. It's now 2, 21. If you look at the shape of this, this is 2, 21. I want to multiply this X comma transpose with another matrix, which is say X. What should be the resultant shape? 2, 21 multiplied with 21, 2.
2.
2, 2, right? Okay. But please note that you cannot use star here. You have to use a function which can do matrix multiplication. Star does element-wise multiplication. So it requires that the matrices have to be of the same size. They are not of the same size. One is 2, 21, another one is 21, 2. Please note that star does only element-wise multiplication. Okay. So if you want to multiply two matrices, go to NumPy, use MaxMul, matrix multiply. Okay. and you can multiply these two matrices. This will give you your 2 cross 2 matrix, which is this. Okay. Now I have to take the inverse of this. So how to take the inverse? So in NumPy, in linear algebra, you have the inverse. Okay. And you can pass this matrix X transpose X multiplied, and this is the 2 cross 2 inverse. Okay. Now I have to multiply this with what? X transpose again. So you will write np dot maxmul, the inverse multiplied with this X transpose. So you can simply say X dot transpose. So this is X transpose. You have to multiply it one more time with Y. Okay. So I will say let's multiply it with Y train. Okay. And just write one more time np dot maxmul outside. Can you see that? Okay, these are the two thetas that we had. Do you remember?
Yes.
Okay. I mean, if you remember the value 9602 and 25235. Okay. 9602 and 25235. So this is just to show that both solutions are equivalent. Okay. But this solution has an advantage. This solution has an advantage. The advantage is it can be applied to multivariate data also. This particular solution can be applied to multivariate data also. That can only be applied to univariate data. Am I clear?
Yes.
Okay. How about others? Are you able to follow? Like one person is following. How about others? So this is just to show you what we studied, right? Is actually done by these functions. And you might use these functions, matrix multiplication and covariance, variance, when you are computing statistics. Yeah. So these are reasonable. There is a reasoning behind it. Okay. So this is it. So this is just to show you, okay, what we discussed, right? We will do gradient descent a little later, the implementation of it in today's session or maybe tomorrow's session. But I have to discuss a few things first. Okay. Now, let's say I will take a multivariate data set. Can I take that breast cancer data set now? We saw one breast cancer data set, right?
Diabetes data set.
It was it diabetes? Okay, I don't remember. Okay, just let me see. Okay, it was a regression data set where we had to predict the impact of diabetes. Yeah, this is the one. Okay, so I'll be using this data set to predict the onset of diabetes, like how much is the impact has been. Okay, so let's load this data set. So we are now doing multivariate regression. Okay, we are now doing multivariate regression. Okay, and let me call it multivariate linear regression. Okay, so I'm going to load this data set. Do you want me to load something else, something new, or is this fine?
Something new.
Can you repeat please? New data set or this one is fine?
New one.
New one? Okay, I'll take a new one. Maybe I'll take a bigger one. Okay. So this is another big data set, which is this. This is called as California housing. Let's use this one. I'll describe what this data set is. Okay, let me just load it first. So this is your data set. And let me load the data, the features. So this is your features. The process remains the same. Okay. And the output is this dataset.target. Okay. So if you want to see how many features are there, you can simply type x.shape. Okay. These are 8 features are there in this. Okay. I want to confirm something, okay, with you guys. So let's first see the description of this data set. You can see it has 20,000 samples approx. Okay. So this is the data set that we have. We have 20,640 samples. The data set is called as California housing. 8 attributes. The attributes are, so I'll tell you about this data set. So what we are going to do is we are going to predict the house price. Given some features, our objective is to predict how costly a house is. And the prices are in dollars, by the way. Okay. So these are the features. So you can say that we are trying to predict the house price in a society. Okay, so if there is a society, we are going to predict how much costly a house would be in that society. Okay, so 20,640 societies have been considered in this data set. So when you see median income in a block group, this means that in that society, what is the median income? Okay, median house age in a block group. So what is the median house age? How many years it has been in that society, like for different houses, and you are taking the median of it. Okay, how many average number of bedrooms are there in that society? Average number of bedrooms per household. So these are rooms and these are bedrooms. Sorry, this how much population is there, and how many members on an average, and the longitude and latitude of the location. Okay, so all these features are numeric. No feature is categorical. So using these features, I have to predict what is the house price, and the house price is given to you in dollars, in thousands of dollars actually. So whatever is the price shown to you, that is going to be multiplied with 100,000. Okay, that is going to be multiplied with 100,000. Is that clear? Yes, people. Is the data clear to you?
Yes.
Okay. So I'm going to put everything in a nice data frame. Let's put everything in this nice data frame. So X is the data which I took. My column names can be obtained from dataset.feature names. So this is the data. Okay, 20,640 rows, 8 columns. Okay, let's put it into this. Say, let me call it input. Okay, this is my input. Okay, and let me just print input.shape. Okay, or maybe say input.head is fine. Maybe say just top 2 features, top 2 rows. Okay, so this is the data that I have. I'll show you the descriptive stats. Okay, so I'm showing you the stats about this data set. What can you say about the minimum and maximum? Are they the same or different for different features?
Different.
Very different, right? You can see the minimum and the maximum values, very, very different. Okay. Maybe I'll just print it. Okay. So I'll take the transpose of this and I'll print it side to side. Okay. So I'll just printing minimum and maximum. There is a lot of clutter here. Okay. So you can see minimum and maximum right now, and you can see they are very different. Now, if they are different, what I can do is I need to scale the data. So for linear regression, I advise you to do standardization. Okay. For linear regression, I advise you to do standardization. Okay. But you can do normalization also. That will also give you almost the same results. Okay. So let's first split the data. Okay. I'm going to split it. So I'll just use the previous function that I created.
So one question on
Yeah.
what do we decide the scalar, whether it's to be a normalization or
For linear models, you should prefer standardization. For all other models, go with normalization. For linear models, see all the functions that you will study in this library, linear model. Okay. Linear regression is coming from this library, linear model, right? Yes or no?
yes.
So all the functions that you see in this library, you will use standardization. You should use standardization. I mean, you can use normalization also. Nobody stops you. You will see that standardization will give you as good as results, sometimes better. Okay. All right. So from my experience, I'm just telling you this. Yeah. Okay. So my data is in my input. Okay. So this is my input. My output is in Y. Okay. My output is saved in Y. See, this output is saved in Y. Okay. And I'm taking 30% data in testing. Okay. So this is okay. This is done. Let me see how many samples are there in training out of 20,640. So around 14,448. And in the test, they are this much. Okay. Now I'm going to scale my data using standardization. Let's see that. So let me just scale it. So go to pre-processing, import standard scalar. Standard scalar. Okay. See, the syntax of every function is almost the same if you remember. Okay.
Model preprocessing.
Yeah, sorry, I will just change it. Thank you. Otherwise, you'll throw another error and I'll just recreate it. Okay. So first fit it onto your train. So it computes minimum and maximum for all the train features. And then you will transform the training set. So this will give you transformed data, transformed features of the train set. Okay. You can call it, let's say, standardized features of the train set. Okay. And standardized features of the test set can also be obtained using the same transformer, using the same scalar. Okay. So this is done. Okay. 1 second. What does it say? Sorry. My bad. What am I doing? Okay. So in SQL preprocessing, you have standard scalar and you have done the standardization. Okay. So standardization, so feature scaling is necessary here because the ranges are different. Let's say as the scale of the feature is different. So let me say varies. Okay. All right. So I've done the scaling part. I'll maybe now train a model. Okay, let's call linear regression. Let's train a model onto this, onto the transform data. I call it as standardized data. And the output is ytrain. Please note that standardized data has 8 features. Okay. So the model is trained now. And if you want to see the intercept, so this is your theta naught. This is your theta naught. This is your coefficient. Okay. 8 coefficients because you have 8 features. Okay. I want you to see this. Okay. So let's say I have a sample from the test set, which is this std_x test. I'm going to show you the first sample. Look at this. This is the first sample. Okay. See, how do you predict? This is the first test sample. Can you tell me how do you predict?
Theta 0 plus theta 1 into x1 plus theta 2 into x2.
Absolutely spot on. Okay, theta 0 into theta 1 x1 plus theta 2 into x2 and so on till theta 8 into x8. Okay, this is what we have to do since we have 8 features. Okay. Now, I want you to see this carefully. Okay. So theta 0 is what? This term, right? Model.intercept. Can you see that? Okay. I want to multiply theta 1 with x1. Okay. This is your theta 1, right? Look at the shape of this. This is 8 comma. Okay. This is 8 comma. So if I make this, okay, please listen to this very carefully. Okay. If I and look at the shape of this first sample also. Okay. Look at the shape of this first sample also. Okay. This is also 8 comma. Okay. So what I'm going to do now is carefully see this. Okay. Both are 8 comma right now. Okay. Both are 8 comma. So I'm going to first reshape them. Okay. I'm going to reshape it as 1 comma 8. Okay. I'm going to reshape this as 1 comma 8. Okay. Look at this. You have reshaped it into 1 comma 8. And this is reshaped into 8 comma 1. Okay. If this is reshaped into 8 comma 1, sorry, I missed a bracket here. Okay. Now, if I multiply these two matrices, can you tell me what would you get? Matrix multiplication. 1 comma 8 multiplied with 8 comma 1, what would you get?
1 comma 1.
So it's a scalar value, right? Can you tell me this value will be multiplied with this? Yes or no?
Yes.
This row is going to be multiplied with this entire column. So what is this? Theta?
This will be theta 1.
Theta 1 multiplied by?
x1.
This is theta 2 multiplied by?
x2.
So can I say this is theta 1 x1 plus theta 2 x2 plus theta 3 x3 and so on. So if I multiply these two matrices, I will get this part. Yes or no? Okay. How do I multiply two matrices? NumPy.matmul. I multiply these two matrices. See, the dimensions have to match, otherwise it will throw an error. Okay. So this is your coefficients. This is your this. and we will get the predicted value for your first sample. Okay. Do you see that this is a prediction? Okay. Through which function you do the prediction, by the way, from a model?
Not predict.
Predict. You will see it will get the same value. So I'm just going to show you intrinsically that is what is happening. So in this case, what is the first feature that first sample that we have?
Test of 0.
X test dot, X test of 0, the first row. You please note that you have to reshape it. Okay. You have to reshape it. Okay. Sorry, it has to be 1 comma minus 1. For one sample, it requires reshaping. Okay. My bad. What's the problem? It says 0 comma 0 is in. Oh, sorry. It's not X underscore test. It's std underscore X test. Okay. Okay. And I need to reshape it into 1 comma 1 second. Yeah. Can you see you get the same thing? Yes, people. For one sample, you need to reshape. For many samples, you don't. Okay. Is this clear? Yes, people. Is this part clear? So that is what the predict function is doing. It is computing this theta naught plus theta 1, x1 plus theta 2, x2, and so on. Okay. You can get the predictions for all the samples. So you can predict on all the samples in your X test. So this gives you a prediction for all the samples in your test set. Okay. This is the first prediction. This is the second prediction, and so on. So for all the test samples, it gives you one prediction each. Let's say that, okay, these are predictions. Let's call it spreads. So I'm calling it as spreads. And now tell me which metric do you want me to compute? We are doing regression. So which metric should we use to compute the performance of the model? Give me some evaluation metric. Yes, some. Which one?
Sum of standard errors.
Sum of, we shouldn't call them as standard errors, but let's say sum of absolute errors. Okay. So you can go to sklearn metrics, and so sum of absolute errors is not there, but there is this function called as mean absolute error. What should I do to mean absolute error to get sum of absolute errors?
Multiply by the number of.
Multiply by the number of samples. Okay. Multiply by the number of samples. So this is how you can compute your mean absolute error. So take this actual value which are in y-test, predicted values are here in spreads, and this will give you your mean absolute error. Okay, this is mean absolute error. Let's call it as MAE. And if you want to compute mean squared, you can do that as well. Let's just copy paste this. Okay. Let me first compute, say, sum of absolute errors. So take this mean absolute error multiplied by the number of samples in the test set, which would be x test dot shape of 0. So this is your sum of absolute errors. Okay. All right. And you can do mean squared, whatever metric that you want. Okay. I'm going to do mean squared. Okay. Let's do mean squared as well. Okay. You can compute sum of squared also. Okay. Now, just by looking at it, okay, just by looking at it, do you see it's a reasonable model or it's a bad model? Per sample, you are having this 0.51 as the error. Per sample, if you think about it, let's say per sample, you're looking at mean squared. So per sample, your error is around 0.51. Is it a good thing or a bad thing?
Good model.
It's a decent model. I mean, you can check the R2 score as well if you want. Okay. It's a decent model. Okay. It would be fairly high. It would be around 0.9192, something like that. Okay. No, I can't comment on it. Sorry. Yeah, because I cannot visualize it. Sorry. I was trying to relate it to the previous data. Okay. I can't comment on it, but it seems reasonable. Okay. Y-test and spreads. So around 0.609. It's a decent model. Okay. Higher the better. This is higher the better. Okay. Close to 1 would be the best. Okay. So it's a decent model. Now my question is this. You obtained the model, linear regression model. You found out the results. You can say, okay, this is how good the model is doing. And this is kind of a, you can say, an emulation of what it would perform in the real world. This is like a guess that how this model will do in the real world. So its performance on the test set is going to tell you how this model will do in the real world. On an average, it will give you an error of 0.5165, the MSE error of 0.5165. That is what the test error is telling you. Okay. Now I have a question. I want you to look at all these coefficients. Okay. I want to look at all these coefficients. Okay. I will put it nicely in a data frame. Okay. I'll put it nicely in a data frame. So these coefficients are here. Okay. Put it nice. Let me give column names also. Let's say column name is say coefficients. Okay. I will give indexes as feature names so that you can see for which feature it is. Okay. Okay. All right. You can see this, right? So I have a question here. Please listen to this carefully. So this is how you're doing the prediction, right? Theta 0 plus theta 1 x1 plus theta 2 x2 and so on till theta 1, theta 8 x8. Okay. My question is this. What is the range possible for the output? In what range the output can be in general? If you substitute different values of x1, x2, x8 in this function, what it can lead to? I'm going to define the range of this output. What can be the range of this output? Can someone comment on it? Can it go up to infinity? A very big number? Depending on what you have in x1, x2 up to x8, can it go up to infinity? Yes or no?
For this,
Possible, right? I mean, it depends on what you substitute in x1, x2, x8, right? So it can go up to infinity. See, it's a regression output and it can go to the negative infinity side also. So your output can be between minus infinity to infinity. Okay, so depending on what the values of the features are, it can generate an output in minus infinity to infinity. Okay, so please note that the prediction, okay, this prediction, okay, the predicted value, because you're doing regression, can be between minus infinity to infinity. Okay, now I have a question for you guys. Okay, I want you to tell me, let's say if I look at, so please note that all features have been standardized, right? They are almost in the same range. Okay, most of the values will be between -3 to 3. I hope you remember why they will be between -3 to 3. We discussed about this, right? And k-nearest neighbors.
yes.
Okay, so most of the values are almost in the same range. Okay, my question is this. Let's look at a feature like this, median income. Okay, so median income is the, let's say this first feature, which is this x1. Okay, so I'm talking about this x1, which is this median income. Okay, which is this median income. Okay, this has a theta of, so it's the theta 1 is this. Okay, if I look at, let's say the feature x2, which is your house age. Okay, this is your house age feature. The theta 2 is this much. Okay, or maybe let me take another feature, let's say, which is kind of negative, maybe this one. Let's say this is the latitude feature. Latitude. So latitude seems to be x7. Okay, and theta 7 is this much. So I just want to compare these two features. Can you tell me which feature is more important when you are making a final prediction? Is it the latitude or is it the median income? Out of these two, which feature will contribute more in the final prediction? Which will drive the output more?
Latitude,
Why?
magnitude of this feature is more.
Magnitude of the theta is more, right? So can I say that? Okay, can I say that the magnitude of the magnitude of the coefficient? Okay, the magnitude of the feature coefficient. You're right. The magnitude of the feature coefficient. I mean, besides the importance of the feature.
Yes.
Okay, this concept is called as interpretability. You are able to interpret the model in terms of the coefficients. They are the weights of your features. Okay, this concept is called as model interpretability. You are interpreting the model. What is happening? Which feature is getting more importance? Which is driving the output more? Okay, this concept is called as model interpretability. So in the case of linear regression, you can say that the interpretation is, see, different models have different interpretations. So in the case of linear regression, the magnitude of the feature coefficient. So in the case of linear models, I can say the magnitude of the feature coefficient tells you how important the feature is. Okay. All right. Is that part clear? Instead of saying decides, it says indicates. Okay, indicates the feature importance. All right. See, kindly excuse me for my misspellings. If there are any, you can just go. I change it in the notebook later on. Okay. So I hope you have understood this model interpretability. So if I ask you, can you tell me which feature is like the least important? You look at the data. Which feature is like the least important right now?
Population.
Population, right? So I'm going to do something. Okay, I'm going to do something. Please listen to this, or maybe please see this very carefully. So I'm going to first. So I'll just push this above. Okay. So what I'm going to do now is, instead of looking at the coefficients, I'm going to look at the absolute, the magnitude of the coefficients. So NumPy absolute can tell you the absolute values of the coefficients. You can see this here. Okay. So I've done the absolute of everything. And now I'm going to sort it. So in Pandas, the function is sort values. So I'm going to sort it based on these absolute values. So you want to sort this by this column called as coefficients. Okay. Okay, and you want to sort it in a descending order, because higher the feature, more is the importance. So you can set ascending to false. Okay. So can you see which feature is the least important? So as you commented, population is the least important, right? Yes or no? Okay. Now I'm going to show you a process with the help of which you can decide, or you can figure out which features should be kept in my model to make it better. Okay. So I'm going to do a basic discussion right now, and then I'll implement it for you. Okay. Then I'll implement it for you. Okay. The question is this. Since you are saying that population has a coefficient of close to 0, can you say that population will almost contribute nothing? Yes or no? It contributes very minimalistic, right? Does that make sense or not? It contributes very minimalistically, because this is a number closer to 0. You are going to multiply with anything, it will be a very small value, unless this value is 100,000, 200,000, and so on. But all values have been normalized between what? The range is almost -3 to 3. Okay. So it is not going to contribute towards the final prediction. Okay. And even if it does, it will contribute very, very minimalistically. Maybe say 0.00008, something like that. Okay. So the contribution of population is not very high. Okay. So let me say this, and please tell me if it seems reasonable. Let me drop population from the data. Let me ignore population because it has the least magnitude. So if I drop population, I will get 7 features, right? With the 7 features remaining. I will retrain my model on those 7 features. Okay, I will retrain my model on those 7 features. And what I will do now is I will check the test error. If the test error has decreased, can I say that removing population was worth it?
Yes.
Okay. Can you repeat it one more time with the least important feature that you obtain from the 7 features?
Yes.
You can repeat it, right? And when will you stop?
Till there is not much significant difference in the test error.
Test error, right? Till you get, you can say increment in the test error. You don't want it to be high, right? If the error goes higher, you can say that the feature was actually important. So I'm going to show you how to implement this process. And this process is called as recursive feature elimination. You are going to eliminate these features one after the other recursively. Okay. And when do you stop? You stop at that point when the error, you can say, starts to increase. Okay. So this is a feature selection. Okay. There is this domain of feature selection. What feature selection says is this. Okay. The objective of feature selection is to find the optimal set of features, optimal subset of features, okay, that give you the best performance. Okay, you have to find the optimal subset of features from the original features. Okay, this is the objective. Okay. From the original features. Okay, you have to find the optimal subset that give you a better performance. Okay, let's see if we are able to drop any feature or if population is worthy enough or not. Okay, so I'm going to use linear regression as my model. Okay, I will fit onto my standardized data. So after fitting onto my standardized data, okay, I'm going to compute, say, the mean absolute error, or maybe mean squared error. I'll go with mean squared. Okay, I'm going with this mean squared error. Okay, this is with all the features. Okay, this is with all the features. So my model dot predict on the standardized X test. Okay, this is going to give me MSE on all the features. Okay, is this part clear to everyone so far? Yes, people. Is this part clear?
Yes.
Okay. Now I'm going to eliminate this feature population. Okay. One idea is you can drop the feature population like directly from your data set. There is a function which does it for you. Okay. I'm going to show you that function. So you don't have to worry about going to your data set, select, removing population from it, and then repeating this experiment. Okay. There is a function which does it for you. This function is called as RFE. So it is present in sklearn feature selection. Okay, and the name of this function is RFE, recursive feature elimination. So what this RFE does, it asks you for your linear regression model. Okay, it asks you, one second. So it asks you for your linear regression model. So this is your linear regression model. On the basis of the linear regression model, the coefficient it returns, it will decide how many features to keep. So if I want to drop one feature, how many features I want to keep?
7.
7. Okay. So let me just show you. So it will select, okay, these 7 features for you. Okay. So let me show you how it works. So you can see this RFE. You can fit this RFE to your data, which is in standardized X-train. And the output is Y-train. Okay. One second. It got an expected argument. Num features to select. Okay, let me just see. Okay, what is this name here? Okay.
And rather than hard coding it to 7, can we do it using shape? Because at times we are not sure of the number of features.
Yes, you can put any number here. Any number here. I'll put shape here. I'll put shape here. Okay, just a second. Okay. I just want to see, like, if I'm forgetting the feature argument. It's num features to select.
N features.
N features to select. Okay. All right. Okay. All right. Let's see this. So if you want to select one less feature, right? So you can say X or in this case, you can say standardized X-train dot shape of 1, which will be the number of features minus 1. Is that part clear? We are removing, keeping one less feature, right? Okay. Keeping one less feature. Is that part clear?
Yeah.
Okay. Now, please note this. If you keep, let's say here 6. So what this function does, please note this carefully. What this function does, so first it finds out all the coefficients, takes the absolute, figures out which is the least important. It drops that feature. Then on the remaining 7 features, it will retrain the model, finds the thetas, whichever is the least important theta will drop that. Okay. So essentially what it is doing, it is looking at the coefficients in each step. So it retrains and finds the coefficients in each step, discards the least important feature. Okay. Please note that the model is retrained. It is not dropping. So if you write 5 here, it is not going to drop 3 features in one shot. It will drop only 1 feature in one shot. Okay. And after dropping that feature, it will retrain the model on the remaining features because the coefficients will get updated. Okay. So it is not necessary that, let's say in the first step, if population gets dropped, it is not necessary that average occupancy will get dropped in the next stage because the coefficient will get updated. It is quite possible maybe house age will be dropped next in the next step. Okay. It's not necessary that these three features will be dropped one after the other. Okay. Now, since I'm keeping 7 features, if I ask you, okay, you want to keep 7 features, right? Assume that the 7 features which are kept, they all have a ranking of 1. So assume that those 7 features pass. So what should be the ranking of the population feature? You are ranking these features. Okay. What should be the ranking of the population feature?
4.
How much?
4.
Why 4?
3 people.
So think. Okay, I'll repeat my sentence. So you want to keep 7 out of 8 features. So when you compute the ranking, right? Let's say that's all 7 people get a rank of 1. What would be the rank of the feature that got eliminated?
2.
2, right? Okay. So this gives you a ranking of all the features. So wherever there is population, you will see a 2, and all those features which are important, they are given a ranking of 1. So 7 ones will be there and 1 2 will be there. Okay. So I mean, if you want to know if it is the population or not, you can compare it. So I will put the ranking along with the feature names. Let's see this. So this is my data frame where I'm putting the ranking. Okay. And my index name is the dataset.feature names. And my column names is the ranking. Okay. Which one has a 2?
Population.
That is what you dropped. Okay. Now I'm going to show you, let's say if I repeat this process one more time. Okay. Let's say if I repeat this process one more time, I'm going to keep that 2 now here. Okay. So I'm now keeping how many features?
6.
6. So what would be the ranking of the feature which got dropped first? So how many values will get a 1 at the end?
6 values with 1 value with 2, and 1 value with 3.
So which value will have a 3? Population. That much you know about, right? That much you know about, because you know that in the very first stage, which is the least important feature? Population, right? Always population will get dropped first, right? Will get dropped from the 8 features, the original 8 features. After you retrain, you do not know the coefficients, right? So I'm not sure which second feature would be dropped, but the ranking 3 would be for sure with population. But I will have to see which was the second feature. It is not guaranteed that it will be this average occupancy. Please note this, because the model is retrained. Okay. So I'm going to show you, okay, what gets dropped. Okay. Which 2 features are not important? Let's see this. Okay. Can you see that population is 3, and in this case, it was average occupancy only. Okay. In this case, it was average occupancy only, but please note this can change. Okay. This can change. Okay. Maybe I'll show you for last 3. Okay. Or rather, let me keep, let's say maybe last 3 is fine. Okay. Last 3. Okay. So look at that last 3 features. So what were the last 3? Population, average occupancy, and house age. Are they the ones that are dropped? Population, average occupancy, and house age. Yeah. So unfortunately, in this data set, the sequence is followed. Okay. In this case, the sequence is followed. Okay. But please note that it might change depending on how the features are getting dropped. The coefficient will get updated. Okay.
So if I do it recursively, first time first recursion, I know population will get the highest rank. In second,
so then you will retrain a linear regression model. You will get 7 updated coefficients.
then my ranking will again change, and it's not necessary that average occupancy.
Yes, it's not necessary that average occupancy will be dropped.
Here you can get 1 rank as 1, the average occupancy, and some other feature with rank 2.
It depends on like which feature has the least one, right? So whichever feature has the least importance, right? That will be assigned a ranking of how much? 3, if you are dropping 3 features, right? Thereafter, you will do it one more time, retrain the model, remove the 2 unimportant features that you have eliminated, retrain the model, update the coefficients. So in this case, you see that house age was the one that was remaining. So house age got the least importance. Luckily, the sequence that we have, right? If you see this last 3, These are removed in this sequence. Okay. But it is not necessary this will happen.
Assigning a rank is also a recursive process.
Yes.
First recursion. another rank.
Okay. Think about this. Currently, so I know that I'm going to drop, say, 3 features. So how many will get a 1 at the end? 5, right? Yes or no? That part is for sure, right? I mean, if I'm going to have 5 people left out at the end, so 5 people will have 1. The 1 which would have been dropped, I know that its ranking is going to be 4.
Yes.
The 1 which was dropped after is going to be 3. So it's a fixed thing, right? Even though you are doing this process recursively, I can even tell you like what the rankings would be. Yes or no? I just need to know what the feature is. I will just assign that ranking to that feature.
Okay.
Does that make sense? Okay. So, see, in any case, did I compute the test error as of now? I did not, right? Did I compute the test error? I did not. Yes or no? Did I compute the test error anywhere in this case? No, right? I did not do that. Okay. So I'm going to include that portion in this bit of code. So you can see whether dropping population was worth it or not. And then we will check whether dropping, say, population and this second feature was what? This average occupancy, whether dropping these 2 were important or not. We will also see whether dropping this house age was important or not. So we will go one after the other. We'll try to drop these features one after the other, and then we will see if we get an increment or not. Okay, so we'll start to do that. Okay, let me just show you for one first. Let me drop this population feature and let's see if it helps or not. Okay, so I know that if I just keep it as 1, okay, this will drop the population feature because its ranking is 2. Okay, so if you look at this ranking, right, population has a 2 right now. So RFE has another thing which is called as support. Okay, and what this support tells you is this: whichever features have a 1, they are true. Whichever feature is not 1, that is a false. Do you see that? Whichever feature has a 1, that is actually a true. Whichever feature is not 1, that is a false. Basically, that feature I need to drop. See, this is as good as saying, this ranking array is equal to 1. Both are the same. Both are the same. Can you see that both are the same or not? Yes or no? Wherever there is a 1, it's a true. Otherwise, it's a false. Now, why am I telling you this? Because I can use this to select the features. Am I clear? I can use this array, the true false array, to select the features. Okay, let's say this is my data, std.xtrain. I want to select only those features wherever there is a true. You want all the rows, and you just pass this RFE support. It will only keep those features wherever there is a true. Let's see this. If I print the shape of it, let's assume that what I said is correct. What would be the shape of this? How many features will be there?
7 features.
7. Okay. So wherever there is a true, it keeps those. Wherever there is a false, it just discards those. Okay. So I'm going to train a model with these 7 features. Okay. So this is my training data. The output is Y-train still. Okay. So I've trained my model and I'm going to compute the mean squared error now. So this was after dropping population. Let me compute this mean squared error after dropping population. Okay. Population feature. Okay. So please note that in the test set also you have to remove that feature. Otherwise, the model will not recognize. I mean, because the model is trained on 7. How can you test it on 8? Okay. All right. So this is the mean squared error afterwards. Can you tell me if it helped or if it did not help? This was the mean squared error before. So this was with all the features. Okay. And this is by after removing it. Did it help or not?
No.
It did not help, right? So population is still important. Okay, it stopped in the first process. Let me do say mean absolute. Okay, let me do mean absolute. Because it depends on what metric you are using, right? Let me do mean absolute. Okay, I'm going to do mean absolute now. So this is with, okay, I have to retrain that otherwise. Just a second. Okay. So with all the features, this is this. I'm going to do mean absolute now. So this is with all of it. Okay. Okay, this is the number. I'll just paste it below. This is with all the features. Okay, and let me compute mean absolute with one less. Okay, let me just run this. Okay, and here I'm going to say mean absolute. Okay. Now, was it worth it to drop it or not with mean absolute?
No.
With all of it. And this is after dropping population. You can see that population is still important. Yes or no? Okay. So this particular method for this data set tells you that population is also an important feature. Okay, so you cannot drop it. Maybe you can try with artist score. This is just to show you, okay, it might be possible. Okay, it might be possible that for some of the features, okay, so this is the artist score with the one feature dropped. I'm going to show with say all the features. Sorry, let me compute the artist score. So this is this much. This is with all of it. Okay, let's see if it was worth by looking at artist score.
No.
No, right? R2 is higher the better. Okay. So I mean, this is just to indicate that you can try different metrics, and if it has an increment in the performance, you go with that. Okay. Otherwise, you don't. So you will stop here. So shall I take a different data set and let me tell you, okay, so that I can see, okay, some features are not so useful. Shall I take a different data set and probably show it to you?
Yes, yes.
Okay. So what I'll do is probably I'll create my own, and I will put a condition that, okay, these many features are not informative. So that when this method runs, you see those many features are dropped. Okay. So I'm going to create a data set of my own. So in this case, it tells me, okay, it is not worth it to drop. Okay, any feature. So let's create my own data set. So I'm going to create my own. So you can use this function called as make regression. Okay. This function can help you create your own data set. Have you seen this before, by the way?
No.
Okay. It's just an easy, easy function. Provide the number of samples, provide the total number of features. Let's say I'm going to use, say, 20 features. Okay. I'm going to say the number of informative features are, so out of these 20 features, I'm going to say number of informative features are maybe say just 5. And the remaining features are not so important. Okay. So out of 25 are important. Okay. I'll give a random state so that you also get the same data set. Okay. And this will give you two outputs, X and Y. Okay. Now that my X and Y are ready, I'm going to split it with the help of train test split. So I'll just take this train test split. Second. So I'm taking this train test split. Then I'll standardize. Okay. 30% of data I'm sending to testing. So how many samples will be in test? How many samples will be in test? 300. 30% of 1000. Okay. Okay. So I'll be standardizing now. Let me standardize. One second. So I'm going to standardize it. I'm just copy pasting from what I have written earlier. I mean, I don't have to type again and again. Okay. So after I standardize, okay, I can compute the performance on the entire model, like with all the features. So computing the performance with all the features. Okay. So I'm computing the performance with all the features. Okay. Which metric do you want me to compare?
R2 score.
'R2 score. So let's take this 'R2 score. Okay. So I'm computing this R2 score on the standardized test set. So this is with all the features. Okay, this is with all the features. Okay, now what I'm going to do, I'm going to just paste this R2 score in a list called as R2s. Okay, I'm going to make a list called as R2s, and I'm going to append this R2 score, okay, in this list of my R2s. Okay, so this is your R2s, by the way, right now. Okay, which means it is a 1. Okay, this R2 is a 1. Okay, all right, does that make sense? This R2 currently say it's a 1. Okay, so which means that with all the 20 features, R2 is a 1.
You already have a good model.
We have a good model. Okay, because okay, 1 second. Let me see if I can. Let me see if I can add noise to this make regression. Okay, there might be an argument which can help me specify if I can add a noise to this regression data set. Let me see. Okay. Yeah, there is this noise, right? So let me induce some noise in this data set so that I don't get the best R2. Okay. So I'm going to induce some noise. Maybe say, I don't know what this number signifies. I'm going to just say the number is 0.3. Okay, maybe I'll add one more, say 0.8. Okay, maybe say let me just say, okay, the number of informative features are just 3. Okay. Let's add 15. Okay, 15 is maybe say 35, 30. Okay, so you can see that R2 score is decreasing now with increasing noise. Okay, so my 3 informative features are there out of 20. Okay, so my R2 score is this much with all the features. Okay, now what I'm going to do, I'm going to write a simple bit of code so that you can see if I drop 1 feature, what happens? If I drop 2 features, what happens? If I drop 3 features, what happens? And then we will see which is giving me the highest R2 score. Okay, so let me just run a for loop. So before I run a for loop, can you tell me what will this print? So if I go do it like this, range of this std extrain. Okay, first let me please tell me what this prints. Std underscore extrain dot shape of 1. What is this value?
20.
20. Okay, absolutely right. If I run it like this, okay, range of std extrain, I go up to 0 with a step size of -1. What will this print?
20, 19, 18, 17.
What will be the last value?
Last value would be 1.
1. Okay, last value. Sorry, missed something. Yeah. Last value would be 1. Okay. All right. So what I'm going to do now is, okay, I'm going to first keep these many features 19. I'll just subtract a 1 from it. Okay, so I'll just keep 19 features in the beginning. I will compute the R2 with it. Then I will keep 18 features. I will compute the R2 for it. I'll keep 17 features. I'll keep the R2 for it. Okay, so I'm going to run a for loop like this. For j in this range, okay, sorry, for j in this range, let's use our model to be linear regression. So our model is still linear regression. Okay, let's call this recursive feature elimination. Let's call this recursive feature elimination and fit it with these many features. So I'm going to call this recursive feature elimination and I'm going to fit it with these j features. So can you tell me in the first iteration how many features would be kept? In the first iteration, how many features will be kept?
19.
19. So for those 19 features, what I'm going to do now is, okay, I'm going to train a linear regression model, okay, on those 19 features. So I'm training this linear regression model on those 19 features, okay, and storing the R2 for that. Storing the R2 for that. So I'm training that linear regression model on those 19 features, computing the R2 on that, and I will put it in my list of R2s that I created earlier. Okay. So how many R2s will I get finally? Let's say from this for loop, how many R2s will be there?
From this, it will be 19 and then
19, then 1 will be ours, so 20. Okay. So let's see how many R2s we get. Okay. So these are all the 20 R2s. Okay. Do I want to find the best one or the least one?
Best one.
Best one. So let's find the best one. Assume that the first value is the best one. What can you say about the number of features here?
All the features 20.
All the features are important, right? So let's see what is the maximum value of R2s. So this is the maximum value. I want to know at what feature it is. Okay. At what index it is. So let's say if I subtract the number of features from it, can I say these will be the optimal number of features?
Yes.
I mean, if I find the index of this location, so index will be like this, right? R2's dot index of this location. So if it was 0, can I say all features were important? If the maximum value was at index 0, can I say all features were important? Yes, right? I'm subtracting 20 from it. 20 minus 0 will be 20. Now let's see at what index it actually is. Okay. 3. What did I say in my model? How many features are important? So do you realize that now this actually works? When I created this data set, how many features did I say were actually informative? 3. And you can see that at the end, it keeps just 3 features. So if you want to know what those 3 features are, you can just type RFE.ranking. Okay, sorry, ranking underscore. So 3 ones will be there and everything else will be 70. Okay. You can see 3 ones are there. This is one. Maybe where is the other one? Do you see any other one? Oh, so this is not the, you have to retrain the model. This is not the last one. Okay. You have to retrain it. Just a second. So you can specify 3 here because the 3 are the optimal number of features to keep. And then you can print the ranking. So these 3 features, this one, and this one are the 3 most important. Okay. In the data set. Okay. Is this clear?
So
Yes.
this RFE function, it's doing the job of building a linear model, calculating the thetas, sorting it, removing the least weighted theta value. These 4 functionalities this RFE is doing in one single
shot. Yeah. So RFE just removes the least important feature at every step. Okay. Trains, sorts, removes the least important feature at every step.
Okay.
Okay. And then we are checking the performance, whether it was helpful or not. So I did it for everything. Okay. I could have stopped it, right? I could have stopped it as soon as it started to dip.
Yes.
Okay. I could have stopped it. Okay. But I just showed it for everyone. Okay. I just showed it for everyone. So like even if you keep one feature, what is the performance? So that's how you can do this as well. But if you have lesser number of features, you can put a break. As soon as your RFE starts to decrease, your evaluation metric starts to decrease. The performance starts to worsen. You stop. Okay. Is it not clear? See, please note that I'm looking at the maximum value here because it is R2. If it was mean squared error or mean absolute error, I will look at minimum. Okay, because R2 is higher the better. Okay, any questions? You can actually define this instead of 20, say that this is nothing but std of xtrain dot shape of 1. Okay, to make it generic. Okay, that will be the number of features, right, for any data set. Okay. So you can make it generic if you want to do it like this. Is this clear? Shall I go ahead? Yes, people. Shall I go ahead?
Yes.
Is it too much for the day? I have so much to discuss. Okay. This is just the beginning. This is something which is like quite straightforward, but now we are seeing the implementation for it. Okay. Anyone has any questions? You can write to me or you can even speak up. You can take a 2 minutes break and come back. Okay. I'll show you the next topic then. Okay. Do you want a 2 minutes break or shall I continue?
Yeah, we need a breather.
Okay. Let's take a 2 minutes break then.
Because like it's
So
like
let's start at say 32. Okay, I'll start at 32. So
yeah,
please
better.
come back, go to the washroom, come back quickly, and then we'll start. Meanwhile, if you are still here, you can discuss with me. See, I request everyone to participate if you want. Okay, I cannot read minds.
That's true, Sanatan. But like, what's the like expected time of our course and like?
See, I can tell you about the time that I will need. I cannot say for the rest, right? So, like if you are with me, we will have. So I'll count the number of hours that are assigned to me. Just give me a moment. See, it is on you guys as well, how quickly you are able to catch up. So if you give me all the 2 hours on the dot, and let's say maybe a few extra 10, 20 minutes at the end, then I can perhaps cover everything on time. Okay. But it might spill over, maybe say 2 to 4 extra sessions, so maybe 1 week extra. So this is your curriculum. Okay. See, I'm spending a lot of time in making you guys understand what is going to be used very, very frequently. So I will not repeat these things for the other module. So the other models that you study, right, you will have to do these things as well. So I'm doing it right away in the very beginning. So when you're training these other models, you remember all these things and you can do it on your own in your free time. I will just show you the function of the other models and we'll talk about, okay, what they give you, what are the hyperparameters. And then you can run this function again, like grid search CV, randomized search CV. If you want to do different types of cross-validation schemes. So you will reuse those functions again. Okay. I will just show you how to tune, I mean, what parameters to tune and all that. Okay. We'll not do much after this. So our discussion would mainly be about like how to tune a particular model. What is it that we need? You already have the methods for it. So I'm covering everything in the beginning. So for the last, I wouldn't say for the last few weeks, it will not be much time. Okay. But still, let me just take a quick overview of your syllabus. So we are currently, today we discussed this feature selection interpretability. So we are at this stage, okay? We are about to discuss this, but I'm going to discuss certain topics before this, which are important, which are not listed here. Everything else is like covered, okay? There is this topic which you might be wondering, what is expert systems and 6 jars? It's nothing but something that you have studied already, but I haven't defined what those 6 jars are, okay? So after I cover linear regression, I'll tell you what those 6 jars are. What are the important things when you apply any machine learning algorithm? Okay, you need 6 things. Okay, you need 6 things. Rest everything I have covered. Okay, rest everything I have covered. Okay, so let's assume 2 hours for every module. Okay, so I mean basically for every session 2 hours. So you are here right now. So 2 and 2, 4. So 6, 8, 10, 12. So I'll be teaching up to this point. Okay. So let's say you have 12 hours right now. I mean, from today's session, I would probably take maybe 16. So 4 more weeks to complete till this point. That is my estimate. You can
check with the coordinator.
Yes. Yeah.
So Sanatan, ideally, like, can we like give it a guess, like September 2nd week? Is that a probability?
16 weeks is September 1st week only. 16 days is, see, let's say if you have 4 lectures per week, right?
Yes.
So it would be a month. So it would be September 1st week only, in my opinion.
So because like we already entered the 2nd week of August.
I understand. Okay, I'll try to finish it. I will even do it before that. It's just that, I mean, there are some topics, right, which everyone can cope up with. Maybe you can, but others cannot, right? I have to keep everyone in mind. So I have to reduce my pace. So I am assuming 4 extra lectures, but 4 is like a overestimate. I may be finishing maybe in the first week of September itself. Okay. Even before that, I might be. Okay. But we will not spill over beyond, say, September 7.
Okay, so the cutoff, like estimate cutoff is like around September 7.
Can you be a little louder, Kiran, please?
Yeah, the estimate cutoff would be around September 7.
Yeah, up to this point. Up to this point.
Yeah, and the last 41 and 42 would be by another coordinate, by another
See who will cover.
mentor.
I'm not sure who will cover these. So there will be again like 4 hours. Okay, 2 and 2 hours.
Yeah, but the mentor would change, correct?
I'm not sure if I'll be the mentor or whosoever will be the mentor. I can't, comment on this right now because, see, Groovy people have a particular, what we say is,
Style of operating.
I can't say style of operating, but they have dedicated mentors for these modules. Like for each of the modules, right, that you see, they have made a pool of them. So maybe this pool is allocated to this pool is allocated to this pool is allocated to this. I am actually in this pool also. Okay, in the module, in this pool. But the reason why I will not probably cover these is my full-time job is going to start in that time frame. So since I have already committed up to this point, I've already committed to them that I'll complete up to this point. I might not spill over because my regular job would start. And I'll not be able to dedicate this 9 to 11 time.
So Samadhan, so you be like in the future, you'll be working as like lead data scientist or something where you're taking up your next assignment.
Can you please repeat in future if?
No, the assignment what you're going to take up in September is that of a lead data scientist in a company.
I didn't get you.
What would your full-time role be?
If I can't hear properly, or maybe it's the same with others. Maybe my headphones, earphones are not that great.
Oh, it's not clear.
It's not clear, right? I mean, it's a little fuzzy.
Yeah, maybe like my internet connection is also kind of fluctuating.
Okay, yeah, go on. It's not fluctuating. See, I believe there is like what we say is a monotone which is happening. Can you please repeat? I'll try to be.
Yeah. See, like what I'm trying to ask you here is like the assignment that you're going to take up in the September 1st week. Is that the role of a lead data scientist in your next assignment?
Oh, so see, let's say if I am assigned to this, okay, I will not be doing these. I'll be doing some advanced projects, not these. If
Okay.
assigned to these, okay. So this is just what we say is tentative projects.
Yeah.
Okay, these are tentative projects because as per the demand of, you can say, the current trends.
Market. Yeah.
So you might see different projects. So I know that some of the projects that these Groovy people are having is one of them is like YouTube harvesting and making recommendations from YouTube data. That is one thing. One of the other projects that they have is like, so they have collected some data in association with PhonePe.
Okay.
So you'll be building some projects which you'll be deploying on a website, so that you can, showcase on your portfolio as well. So like you will post it to your GitHub page, and you can, actually show, okay, this is happening live. So you will probably use applications like Streamlit or Flask to deploy your models. So that is like building a nice dashboard for what is happening, but you'll be deploying it live and anyone can access it.
Okay. Using real-time numbers, is that
Yeah.
what you mean?
Numbers that are incoming. Okay. So it will be like a pipeline that you will build. So that is one other project. If I were to do this, I would do it like for a very hardcore project, not like this. See,
Okay.
background I would say is more of an applied scientist.
Oh, okay.
Okay, so I am more into vision, NLP. I don't do much data science. I build ML applications. So I can talk about like what I have built so far or what I have contributed to, but probably if I do that, I'll need 10 to 20 minutes of time, which I don't think I have right now at this moment. No, because the session will get over by then, right?
Sure, sure. Sanatan, my last question for you today is quickly in a nutshell, can you define like what are your achievements in like project wise?
The achievements like from my side or
Your
like,
personal achievements, like you've done
yeah, I
this
mean,
project like that.
okay, like for the companies that I've worked.
Yeah, or otherwise, like what learnings have you applied practically in a project and like.
Okay. I'll talk about like maybe a bit of about my experience. So I've worked for some service-based companies, some product-based companies. Just to name a few, I've worked for Siemens and HCL for a limited time. And I have also worked for Amazon and Intel as an applied scientist and a graduate researcher. So my roles here, more or less, you can say inclined towards engineering side of it. Okay. So I'm not sure whether you have heard about MLOps.
Yeah, I did.
Training the models from live data and then deploying it with the best possible performance so that your customers can, get the best out of it. Okay. So from that sense, my, roles have been more towards the technology side, not towards essentially understanding the customer requirements. Okay. So I was given a set of tasks by my manager. I have to utilize the best set of tools, you can say platforms that are available, and I had to build a solution for it. Okay. So I would that
basically it would be deployment and implementation. Correct?
Deployment and implementation. Okay. So from that perspective, you can say an applied come data scientist. Okay. See, it's always you cannot skip data science even when you are training models. The knowledge about the data that you have, okay, it's very much important in just figuring out. So perhaps you are wondering, okay, why am I teaching so much maths? Data scientists don't do so much maths. Is that so?
No. We do need it to make our decisions, right?
No. See, I can maybe perhaps understand your perspective also, like why you're asking this, because like from other instructors that you would have seen so far, right? They are more, I would say, inclined towards implementation. Yes or no?
Exactly. So like I'm trying to the reason why I'm asking you so many questions is I'm just trying to figure out like the other possibilities.
Oh, okay. So see, once you graduate, like once you complete this course, right? You can actually apply to other opportunities given the fact that, okay, you have acquired some additional skills. For example, let's say if you want to transition into this ML engineering side, you need to learn just 3 other skills, but learning those skills is going to take time. So one is CV, one is NLP in a little more detail, and one is working on attention and transformers. Okay, but learning those would require another 3 to 4 months. So
that would be like our personal investment in personal time, correct?
Yes. So like when you join an industry, right, they would actually give you the projects on these topics. So nowadays, that is the current trend. So everybody is using transformer-based models to do everything. I mean, what product do you think has become a rage right now?
The electronic payments.
Okay, that is one thing. But electronic payments has been, they have been here for a long time, right?
That's for us in India, but like you see, like
which product, think about from the data science perspective, has revolutionized the world?
The chatbots.
The chatbots. Okay, so it's all about text nowadays. Okay, so this is where the current investment of the entire industry is. So if I were to suggest something that you should do to have a competitive edge, do something which is related to NLP, natural language processing. Okay. Try to learn advanced models that can probably give you an added advantage in terms of your portfolio, as well as something which you have as a niche in comparison to your peers. And that is much more in demand in comparison to any other skill. So even though we'll cover NLP, okay, but it will not be like very advanced NLP that you actually need to crack these tier 1 companies.
Okay.
So my suggestion is, like, when you are done with this course, let's say if you get into a company, right, upskill yourself every time. Don't just become stagnant. Okay, so if you really want to transition into these big companies, you really have to learn state-of-the-art technologies. Okay, and training state-of-the-art technologies is not possible on Collab or your system, or even my system. Okay, that is where the bottleneck is. Okay, so you have to have a cluster of machines, accelerated data science resources. Maybe when I complete this course, right, I'll take maybe one extra session to describe what you can learn. Okay, so that you can really crack these big companies. Okay.
See, Sanatan, like my ultimate aim is to see, like after I acquire these skills, like I want to go into a particular kind of industry. Say, for example, if you take like a entertainment industry and maybe say or the green revolution. This
Okay.
is just like hypothetical example that I'm giving. So I would like to go into the green energy sector because like the climate change and all the
Okay.
transportation is on a changing phase now. We are progressing, like we are graduating to a different kind of thing, right? So
Okay.
I would want to get into that kind of industries.
Okay, I understand that. Let's say if you're looking for a specific job, right, in this sector, my suggestion would be align your projects with that. So in addition to the projects that Guvi provides you, right, do something on your own instead of, asking them to maybe make a custom project for you.
No, Sanatan, like maybe I have to reframe my question. Say, for example, the industry that I'm choosing, I have to reskill and fine tune myself according to that industry requirements. Am I correct?
That is true. See, that is true. But the essential fundamentals, right, the skill sets that you will see in that industry and this industry, they are the same. See, if you ultimately want to end up doing data science in that new sector that you are referring to,
Right.
the underlying things are not going to change, right? But why would they hire you if you have not worked on, let's say, a similar project to what they are working on right now? So I'm suggesting maybe you build some of these projects in similar areas, and you can showcase that, okay, these are some of the things that they will have, they will see the usefulness in you. Okay, so if in whichever sector you want to end up in, align your projects with that. Okay, that would be one of my suggestions. Most of these new sectors that you are referring to, right, they are open to research. So if you can align your project,
Exactly.
you can align your projects with something that has not been done before, or that has been done to a limited extent, and you are building on top of that, you will have that edge, and they will probably select you as well.
See why? Because Sanatan, like let me put it straight on the table. Tesla has opened up its office in Pune, and like they are starting to hire from September.
Mhm.
So like my ultimate aim is to crack that.
Okay. Okay. Maybe I can help you with that, but you have to come up with a well-defined problem statement. Okay. I'll be frank. Okay. I would not like to do it for a single student. I hope you get the point as well. Yes or no?
Yeah, that rings a bell. Yes.
Yeah, right. Okay. So I will not try to formulate a problem statement which would be enticing to you, but maybe not to others. So if others also, and if others do the same thing, then perhaps there is not much in it for you. Do you realize that?
Yeah.
I mean, if everybody does the same thing, do you have an edge over them? No, right? So
Yeah, like I'll be in the group, like one of the group.
I would request you to maybe come up with a problem statement or find a data set, because data set is important. For you to do data science, you need data. Okay.
Right.
So whichever sector that you are targeting, okay, think about how you would scrape the data for it. Okay. Find the resources. Once you have scraped the data, we can have a discussion. I'll tell you what to do. And hopefully, when you graduate from this course, you have that project ready. You can connect with me on LinkedIn. I'll guide you through that.
And on LinkedIn, you're with the same name, right?
Yes, Sanatan Sukhi Jamani. I'm the only person with that name.
Oh, good, easy to identify then.
Yeah. All right.
Thank
Okay.
you, Sanatan.
No worries. Okay. All right. So let's start our next topic. Now, okay, let me ask a simple question to everyone. And perhaps everyone can chime in. So the idea is this. Let's say if I have one feature, how many dimensions do I need to visualize the regression fit? Two dimensions, right? If I have two features, how many do you think I'll need?
Three.
Can you visualize for more than three features?
No.
Okay. So currently the examples that I've taken, let's say if I look at the first example, with one feature, I need two dimensions. So I can actually visualize and make a comment about, okay, which type of model will do justice to this, which would be a good predictor for this data. And I am choosing this function linear regression, right? Because I can see it. What if you have more than three features? So you cannot even visualize. So how do you comment on it? Now, one thing is, maybe you try to fit quadratic functions, cubic functions, power 4, power 5, and so on. And then you see which function is doing the best. Then you see which function is doing the best by evaluating your performance on a test set. You can do cross-validation also. So can I say that if I increase the degree, okay, if I increase the degree of my function, I will be able to evaluate which degree is doing a good job, even though I cannot visualize, but I can still comment based on some evaluation metric. Let's say this particular function is doing a good job or not. Yes or no? Does that make sense or not? See, even though I cannot visualize, I can split my data into train and test. On the test set, I will try to evaluate the performance of a linear model, a quadratic model, a cubic model, and so on. And whichever degree is doing a good job, can I say that that will do a good job in the real world also? Even though I cannot visualize the data.
Yes.
Does that make sense or not? Okay. So now I'm going to show you how to fit quadratic, cubic, and so on. Okay. All right. So imagine I just have one feature for now. So I'm going to now fit a parabola to this. Parabola is a quadratic function, right? Okay. Do you think parabola will do a good job in comparison to linear?
In this case, no.
No, right? So I'm going to show you, okay, maybe, or do you want me to create a data set which is actually kind of parabolic? And I will show you, okay, for that, maybe parabola is better in comparison to a linear one. Do you want me to do that, or shall I show you on this data set alone? Let's say if you want to fit a parabola to this, you will not see good results. Or shall I do it the other way around? I create a new data set which is parabolic, and I will try to fit a parabolic function to that. Which is better? Shall I create a new data set with parabolic points? I mean, points scattered on a parabolic line. And then we will try to fit a parabola to that.
On the same data and show that parabola is not good.
Good. Okay, let's see that. Okay, I'm going to use the same data and let's fit a parabola to this. Okay, so this is the data that I have. Okay, I'll just rerun this because I've used multiple data sets, right? So I'm just rerunning this. Okay, what I'll do is I'll probably keep everything in one cell at the end. Okay, so I'm going to show you how to do polynomial regression with any degree. Okay, maybe I'll not be able to finish it today, but if you guys give me say 10-15 extra minutes, I'll be able to finish it today as well, or otherwise we'll do it in tomorrow's class. Okay. Just a second. All right, so this is the data. I'm going to split it into train and test. And this is how the data looks like. So I'm going to show you how to fit a parabola to this. Okay. So before I fit a parabola, I would like to do a certain thing. So this is the data right now, okay, of your training data. Okay. So what I'll do is I'll just sort the data based on these X1 values. So I want to show you your X train first. Are these values sorted? Can you comment on it?
No, not sorted.
No, right? So I'm just going to sort these values. Okay. So I'll just put everything in a nice data frame. Okay. So let's say this is my X. Okay. This is my X train. Let's call this as my input, or rather, let me call it say S. Okay. And you can call it columns of say X1. Okay. So my feature name is X1. Okay. And my output is this Y, and my output is in Y train. Okay. And I'm going to sort it on, so this is your S right now. Okay. I'm going to sort it on X1. This is necessary while plotting. Okay. If you want to plot for a quadratic function, you will need this. Okay. So I'm going to sort it on this X1. So I can say S dot sort values. I'm going to sort this by X1, this feature X1, and you can sort it in ascending, descending anyway. Okay. So this will do it in ascending. Can you see that it is now in ascending? Yes or no? Can you see that this is now in ascending? Okay. And I will simply assign it. So let's say if I do X1 of this is X1. Okay. The X1 values. And I'm just reshaping it. So let me get the values from it. And I'll just reshape this into this -1, 1. So this is just to ensure that my data in Xtrain is sorted. I don't need anything else, frankly. Okay. So this is my Xtrain data, and now it is sorted. Okay. Similarly, I will assign the corresponding Y train as well. Okay. So my Y train would be, okay, so my output is in Y. Okay, you can call it Y train. You don't have to really reshape it. You can just keep it as it is. Okay, so my Y train is also ready. Okay. See, if you plot this again, will there be anything changing now that I have sorted the data? Do you think anything will change? No, right? It's just that the order of the points in which they were plotted, that has changed. Okay. Nothing will change in the plot. You can actually compare. Nothing changes in the plot. Okay. I just sorted it because I'll be plotting it later. Okay. Now, can you tell me what is the equation for quadratic? What is the quadratic equation in general?
ax square plus bx plus c.
Ax square plus bx plus c. Now, when I'm trying to solve this quadratic equation, I say it is typically equal to 0, right? And I find the two roots. Yes or no?
Yes.
Now, my question is this. When you are doing ML, don't you think you know what x is?
Yes.
Here you are trying to solve for, I mean, in general, in this equation, you are trying to solve for x. In ML, what is it that you solve for?
Coefficients ABC.
ABC. Okay. So can I say this is written as θ2 into x square, or let me call it x1 squared, okay, plus θ1 into x, okay, θ1 into x, your x1 plus θ0. This is what I'm doing, right?
Yes.
Okay. I know x1 squared, I know x1. See, if I know x1, don't you think I'll know x1 squared?
Yes.
Okay. So what is it that I have to do? So I already have this feature x1 in Xtrain, right? Sorry, I already have this feature x1 in Xtrain. What is it that I have to generate? Xtrain,
More array or one more column to my data.
Xtrain
A
square,
square value of Xtrain.
right? I have to do that, right? So I'm going to generate one more, which is called as say Xtrain squared. Okay, this is Xtrain squared. I'm going to concatenate the two. And now then I'll apply linear regression to it. As simple as that. That is polynomial regression with degree 2. Okay. So let me concatenate at axis equal to 1. Okay. And this is the square values concatenated side to side. Is this clear? So this is now your x with degree 2. Let me call it x with degree 2. Okay. All right. Do you want me to show that the results for degree 1 are better? Do you want me to show the results for degree 1 are better than this quadratic? I will also plot the line on top of this. Okay. Let's train the linear regression model quickly. Please give me 5 extra minutes so that you can see what is happening. Okay. So model.fit on Xtrain and Ytrain. Okay. These were the original data. Okay. These are my coefficients. Okay. This is my coefficient. So this is your M value. So can I say this is my M value? Okay. This is your M value. And your C value is then model.intercept. Does that make sense? And if I want to plot the line, what should I do? If I want to plot the line, what should I do? Mx plus c, right? Yes or no? Okay, so I'm going to show you the best line that you get. Let me just keep it above. So this is your data xtrain. The line is m into xtrain plus c. Okay, this is your line. Okay, you can see this is the line that you get. Do you want me to compute some evaluation metric? Which one? Give me one metric. I'll show you that will be higher for quadratic.
Mean square error.
So let's compute mean squared error. Okay. So we'll print this as well, just in case. Okay, for your actual values and the predicted values. So in this case, please note that I have not standardized. Okay. So I'm just going with, I mean, you should have standardized, okay? But I'm just showing you, there's one more bracket needed, okay? So this is the mean squared error, by the way. Okay, let me print MSC also here just to show. This is your mean squared error, okay? All right, for this line, okay, linear function. I'm going to show you now for this quadratic function, okay? So let's fit it onto this quadratic function. So what is my data input? This is x degree 2. So this is my x degree 2. See, scatter plot will not change. What would be this equation? Okay. So first, let me just show you something. Okay. Let me just comment this part out. Okay. So my model is going to be trained on this x degree 2. This is my input. Okay. Now I want to show you something, okay, before I touch this, okay. How many coefficients do you think will be there?
Total 3, 2 theta.
Coefficients how many? 2, right? Theta 1 and x1. Sorry. Just a second. What's the problem? What does it say? What did I define it as? Oh, I didn't run it or what?
Degree underscore 2, I think.
No, I didn't run it. Okay, that's the problem. Okay, so these are two coefficients. So if I print this 0 of this 0, sorry, I have to print just 0 of this. Okay, this is your theta 1. Okay, and let's say this is your theta 2. Okay, model dot coefficient underscore of 1. Okay, so I have these theta and theta 2, and where will be theta naught? Yes or no? Okay, so I'm just going to print theta 0, theta 1, and theta 2. Theta 0, theta 1, theta 2. Just printing these three values. Okay, these are the three values that I obtain from this two feature set. Let's try to see how the function looks like. And we will compute the mean squared error of that as well. Okay. All right. So fitting on the values. So what is the equation right now? Theta 0.
Theta 0 plus
theta 1 times x train plus theta 2 times
square of x train.
Square of x train. Okay, so this would be your equation. Okay, and you will see hopefully a parabolic equation. See, because you are trying to fit to this data, okay, you are trying to fit to this data, the function is linear, right? Yes or no? Can you see that the data is linear? What can you comment about the theta 2 values? Will it be high or low?
Low.
Low, right? Because it is not actually, the function is, the data is not actually quadratic, right? So theta 2 value will come out to be small. Okay, that's why I said, should I create a quadratic data for you? So you can see theta 2 values will come out to be big as well. Okay, so you might not see much difference between this, okay, the linear, because if theta 2 value is 0, it will converge to a linear function. Okay. All right. So when you are predicting on the test set, right, you cannot do it on the test set. You have to first concatenate. Okay. Because you need the square values as well, right? So you have to concatenate x test and x test squared. Okay. And then you have to say axis is equal to 1. Okay. All right. This is for concatenate. This is for predict. This is for error, and this is for MS. Okay. Okay, this is where additional bracket is there. Yeah. Okay. Just a second. do you realize that, okay, this function is actually quadratic? Okay, let me actually print the previous one also. They are actually very, very similar. Okay, look at theta 0, theta 1, and theta 2. Do you see theta 2 is actually fairly small, around 76, as compared to the other thetas? Yes or no?
Yes.
Okay, it's fairly small already. Okay, as compared to the other thetas. Okay, let me just print this also on top of this, so you can see the difference between the line and this. Okay, I am printing the line also. Do you see that there are two functions being happening? Actually, the orange one is the parabola. It's not very smooth. Okay, it's not very smooth. Do you see that now? I mean, are you able to see there is a subtle difference between the, because orange is going like this. Yes or no? Orange is actually going like this. And what is the MSE? Can you confirm? Is it higher or lower? It's 30589631. It was, let me just print this value for linear. Look at this. Which is higher? Can you tell me? Is it higher for linear or is it higher for quadratic?
Higher for quadratic.
So which means that linear is better, right? Okay. Shall I show you for a cubic as well? Cubic, you might see that it would be like an S shaped. Okay. It will be like first increasing and then decreasing. Okay. Shall I show it to you on a cubic as well? Maybe it is not clear because the data is actually linear. That's why it's very, very close to that line. But I hope you can still see this. This slightly goes here and orange comes below the line and then it goes up the line again. Yes or no? I don't know if you can see this or not because the theta is not exactly that great. Okay, let me show you for cubic and we'll be done with this quickly. Okay, let me show you for cubic. Okay, let me just do this. So those of you who want to leave can leave. I'm almost done. Okay, I just wanted to show for a cubic function. You don't have to do all this, by the way. There are functions for it. Okay, I'll show you the function in the next class. So let me just finish this for cubic. Okay, so this, let me call it degree 3. So I'll just concatenate one more, which is x train times cube. Okay, so I'll fit this. Okay, it will give me 3 coefficients. Let's call it. So instead of calling it as theta 1, theta 2, let me call it say A1, A2, A3. Okay, because otherwise they will replace the previous thetas. Okay, and this is say A0. Okay. So these are your coefficients. So these will be A0. I'm printing them, okay, just to show. These are your coefficients. Okay. Let's print this, all the 3 functions. So I'm printing all the 3 functions. So the third function would be this A0 plus A1 into X1, okay, plus A2 into X2 plus A3 into this X cube. Okay, and here when you're printing the mean squared error, you just have to concatenate X underscore test star 3. Okay. Okay. Now do you see that? Okay, cubic function is very nice. It's like first goes down and then goes up. Yes or no? And can you see cubic is actually doing slightly better than, I believe, even linear. Let's get the linear value. Okay, this is the linear value. Cubic is actually doing a much better job. Yes or no?
Yes.
And you can see that why, right? Because the trend that cubic follows is much better. You can try with degree 4. Degree 4 will have 3, you can say, crests and troughs. So it will go up, then it will come down, it will go up again. So depending on what is the degree, right, there will be like one less roots. There will be one less root. So if your function is degree 2, like quadratic, okay, the number of times it changes shape, right, is only 1. Okay, how does a quadratic function look like? A parabola, right? How many times it changes shapes? It goes down only, right? It goes down and then comes up. So there is only one change of shape. You can say down and then up. Okay. If you think about a cubic function, it will do it twice. It will first go up and then will come down again. Okay, like that. If you have a power 4 function, it will make 3 transitions. Okay, that's how you can visualize it. For this, cubic is better. You can try with degree 4 and so on. I will show you that you don't have to do this, do it like this, that you have to generate cubic features and so on. Shall I show you right away if you have 2 minutes? You can generate these features in one shot and then apply linear regression to it. Shall I show you that there is a function? You don't have to do this manually by doing square, cubic, and so on. There is a function for it. Okay, just give me a minute. I'll just write the function name. Okay, this was for linear, by the way. Okay, so the function name is called as from sklearn.preprocessing. The function is actually called as polynomial features. Okay, so this function can help you generate any number of features that you want. Okay, the only thing that you have to do is provide the degree here. So let's say I want degree 5. Okay, I want degree 5 features. It will go x1 squared, x1 cube, x1 to the power 4, x1 to the power 5. It will also give you x1 to the power 0. What is anything to the power 0?
Intercept that constant.
It is always 1, right? Anything to the power 0. Yes or no? So it will give you 6 features. Okay, I'm showing you if you had 1 feature originally, it is going to give you 6 new features. Let's see this. Okay, sklearn. Okay, okay, I'll just put it in a nice data frame so that you can see. If you look at the shape for it, it is going to be number of samples in Xtrain times 6. Okay, I'm going to just put everything in this nice data frame so that you can see. Okay, so this is the data that I got from this function. Okay, so it will generate 6 new features for you. I mean, one of them is original. So it will generate x0, x1, it will generate x1 squared. Okay, I'll just copy paste this. It will generate x1 squared, then x1 cube. Okay, then x1 to the power 4 and x1 to the power 5. Okay, I want to see this. Now, how do you, on which columns do you apply linear regression? So let's say you want to do degree 5 regression. What would you do? You can take only the first column onwards, right? Take all the rows, take first column onwards. Okay, take all the rows and take first column onwards. You will use this data set and then you can use linear regression on top of it. Okay, so you don't have to write explicitly all the time, Xtrain, Xtrain squared, Xtrain cube, and so on. Use this data set. Okay. So this function can help you generate polynomial features, as sweet as that. Very simple. This is called as polynomial features. Whatever degree that you provide, it will go up to that degree. Okay. Just one last question, please. This is important. Very, very important. See, I chose one feature, right? Xtrain. It was having one feature. My question is this. Let's assume that I had originally 2 features, x1, x2. I want to do polynomial regression with degree 2. Can you tell me how many features will it generate? Think about a quadratic equation with 2 variables. Think about a quadratic equation with 2 variables. How would you write it? A times x1 squared
Ax
plus b times x2 squared. Okay, let's say b times x2 squared.
plus C.
It will be c times x1. Okay, c times x1 plus d times x2 plus e times x1 into x2, right? That will also be there. Plus f. Yes or no?
Yes.
Does that make sense? So how many total number of features are there? And total coefficients are there?
5.
A, B, 6.
1.
6. So these, you're right. There are exactly 5 coefficients, 1 intercept. Okay. So when you use these polynomial features, this will generate a total of 6 features because you can assume that it is generating x0 for f. It is generating x0 for f, which is, you can say x1 to the power 0. Okay. And multiplied by x2 to the power 0. Okay. Is that part clear? Yes or no? Anything to the power 0 is 1, right? See, if it's not clear, tell me. I just need 1 more minute to explain this. Is it clear or not? With 2 features, how many function will this polynomial features generate? It will generate 6 features in total. The original 2 features, it will square them up. It will generate a column of ones, and it will generate a column of for multiplication x1, x2. Go on. Am I audible?
Yes, you're audible.
Yeah, you had a question, Shilpa.
No, actually my mic was not on mute. So that's
Okay, okay, all right. So is this clear, right? Or not?
Yes, it's clear.
Okay. I mean, if anyone else has any other questions, please ask. I'll stop here. Okay. I'm not going to teach anything new now. We can discuss if you want. Otherwise, you can leave. Anyone? So all you have to do is use this function on your original data set, and you will be able to generate as many polynomial features that you want. So polynomial features is nothing but linear regression on polynomial features. Okay, so polynomial regression is actually linear, is doing linear regression only, but it does linear regression on polynomial features. So if somebody asks what is polynomial regression, you should say it is nothing but linear regression only, but with polynomial features. Okay, but with polynomial features. Okay, it performs linear regression, but with polynomial features. You are having power of features now. Okay. All right. Okay.
So
Yes.
there are combinations, degree 1 and feature 1. Then I can have single feature with multiple, like more than 1 degree, and then I can have multiple features with more than 1 degree.
Okay, I'll simplify it. Okay, I'll simplify it. If you had one feature x1, how would you write the quadratic equation?
Ax1 plus b.
Ax1 squared. Okay.
Quadratic ax1
plus let's say okay ax1 squared. Okay.
plus bx1
plus bx1 plus cx1, right? Okay. Plus c. My bad. Okay. Let's say x1, and this is the feature x1 for you. Okay.
Yes.
Now think about you have one more the same for your you have now one more variable which is x2.
Yes.
Okay. Can you write the same thing for this, but use different coefficients. Okay, use different coefficients. So let's say this is E. Okay, sorry, DEF. Okay. When you combine them, don't you think you need one more power for having them both?
Yes.
Okay. So when I combine them, I'll need one more feature which would be with G, which would be for say x1 and x2. Does that make sense?
Yes.
Okay. I hope this part is clear. Okay. Now combine all of them together on the right hand side. Can you write FNC as one constant?
Yes.
FNC can be written as one constant, right? So I can remove one of them.
Yes.
Okay. So I can write this simply like this E. So how many total number of features are there? Coefficients are there? 5 coefficients, right? And 1 intercept.
Yes.
That is what it is. Okay. So when you are saying it's a quadratic equation, you are saying that you will go up to that particular power. So you will have coefficients for degree 0, degree 1, up to that particular power. If you have up to degree 2, you will generate up to degree 2. Okay. For every variable, you have to do it. And then you will have to do it for pairs of variables. Then you will have to do it for triplets of variables.
Yes.
Assuming you go up to that degree. So
yes.
Perhaps this will clear it to you. Can you tell me how many total number of columns will be formed, or total number of coefficients, or you can say total number of parameters that I need if I'm doing quadratic regression with 3 variables? Think about it. Quadratic with 3 variables. Let's say there are x1, x2, x3. Okay. Just think. See, 3 features will be original. Yes or no?
Yes.
And then you will be squaring each of them.
Yes.
So x1 squared, x2 squared, x3 squared, right? 6.
Yes.
You will be having pairs of them, x1, x2, x2, x3, x1, x3.
7, 8, 9.
9. 3 choose 2 will be 3. If you want to generate pairs of features, right, from 3 values, that will be 3 choose 2. That is equal to 3.
Yes.
9. And don't you think you will have 1 for the intercept?
Yes.
So total 10.
Yes. Yes.
Okay.
Got it.
So same way, think about 4. Now this will be difficult.
4 will 1 for each.
One
Then
for each.
1 for square of each. So
Correct.
4, 4.
Then
Then choose
pairs.
any 2 out of these 4s. So it will be 1, 2, 3, 4.
Okay, start with individuals. So those are 4.
Yeah.
And then you start with squares. Those are original 4s. Okay. Then you start with cubes. They are original 4s. Then you start with power 4. They are original 4. So up to degree 1, degree 2, degree 3, degree 4, I have 16. Is that part clear? Okay. 16 plus, I will be generating all possible pairs. So if I have 4 variables, 4 choose 2 pairs.
Yes.
Okay. Then I'll be generating triplets. 4
Hmm.
choose 3.
Yes.
Okay. Then I'll be generating. So the basically the single intercept term is 4 choose 4. Using all of them to the power 0. Okay.
Yes.
So that is 4 choose 4. And now you'll be generating squares of squares. So think of x2 square multiplied with x3 squared. x1 squared multiplied with x2 squared. Yes or no? Those
Yes.
features will also be generated, right? So that's why I said it becomes complicated. The number of features will blow up.
Hmm.
Okay. So it becomes harder. Do you think that you will do it even if you have, say, 30 features with degree 4?
With degree 4.
If you have originally 30 features and I ask you to generate all the features with degree 4, do you think you will do it? Don't you think your computer will not support? The number of columns will become thousands in 10,000s.
Computation.
So we don't typically go beyond degree 3.
Okay.
Not even degree 2 sometimes. Not even degree 2 sometimes. Okay. So we go up to degree 3.
A plus B whole square and A plus B whole cube. That was the last thing that we have learned.
Yes. But you can relate to this now, right? Yes or no? Is it clear now?
Yes. Yes.
Okay, so I'll stop here. If anyone else or you also have any more questions, we can discuss. Otherwise, I'll close the session and I'll upload this.
Another not related to today's session, but actually I was trying to do that practical implementation of grid CV search.
Mhm.
So there is that parameter of scoring, right?
Yes.
So that scoring, it doesn't take R2 square.
No, it takes, you just have to write R2 there. Instead of, okay, so I'll tell you, when you are doing sklearn.metrics, right? When you are explicitly computing them, to write the whole function name. So when you are doing for accuracy, what is the function name? Do you know?
No.
It is accuracy score. So when you are doing mean absolute error, you write the whole thing, right? Without the parenthesis.
Yes.
Okay. But if you are doing it for R2, you just have to write R2. I'll show you. Okay. So when you are looking at these metrics, right? Let me type sklearn.metrics. Okay. So by the way, in scoring, you will write negative mean absolute error or negative mean squared error without the parenthesis. Okay. Yes or no?
Yes. Yes.
Okay. Now I want to show you the scoring parameter. The names are a little different than the actual function names. Okay. Do you see that now? Look at regression metrics. If you want to compute, say, mean absolute error, you have to specify negative mean absolute error. But they are computing the same thing from sklearn.metrics. Can you see that on the right hand side?
Yes. Yes.
So these are the names that you have to pass. So for R2 score, it is just R2.
Okay, got it.
Okay. Maybe I'll share this link in the chat and you can make a bookmark for it. Okay. So just a second. Okay. So the name of the scoring metrics are not the same exactly as the name of the metrics.
Okay.
Okay, but they compute the same thing though.
Okay.
Okay. All right. Okay, I'll just create a new folder here. You guys can leave. Okay. If you have questions, you can stay back. Otherwise, you can leave. So bye everyone. I'll meet tomorrow if no questions are there. I don't see any question in the chat here or there. Okay. So take care everyone. We'll meet tomorrow.
Sorry, hello.
Yeah, go on.
Yeah. Last question. Like while doing linear regression and these models, we are also doing a split of data using test train split.
Correct.
That with k-fold,
Yeah, you should do it with k-fold, not just with this.
like we combine k-fold and nearest neighbors, we can combine k-fold and linear regression models and then.
Yes. Yes. So, I mean, I'm doing it on a single train test bed just to, show you, okay, that on the single split, these are the results. But if you want to really know which degree is better, don't you think you will have to do k-fold?
Yes.
Other results would be biased. Okay. So
and even grid search CV combining with this, with the
parameters here, right? And linear regression.
what?
There are no parameters in linear regression explicitly, hyperparameters. Can you specify anything inside the linear regression function?
No.
But if you are talking about polynomial regression, there is one hyperparameter. What is that?
Degree.
Degree. So you can search on this.
Okay.
Okay. So you can do a grid search on this.
Okay.
Okay. But with linear regression, you cannot, right? Because there is no hyperparameter there.
Okay.
All right. Please note that it will not support degree 1. The degree has to be greater than 2. Yeah, degree has to be greater than 2 because it is polynomial. For linear, you have a function, right? Separately.
So right now, the way we were doing that for our data, we tried with a line, with a polynomial and with a cubic.
Correct.
To decide which fits better.
Correct.
So I can use that grid search CV to decide on the best param.
Best degree on multiple train test splits.
On multiple train test splits, but with polynomial feature and degree as 2. The degree 1, that linear regression I have to do separately.
Correct.
And from 2 to
N, let's say whatever degree you want to go to, from 2 to that particular degree, you have to do a grid search.
Using polynomial feature and degree parameter, doing grid search.
Correct. You have to do everything in a pipeline.
Yeah. Okay. Got
Because
it.
see, first you will be, getting the data. On data, you will generate polynomial features.
Yes.
Or maybe before generating the polynomial features, you would have to standardize also, right?
Yes.
So first standardize, then polynomial features, then you apply the model. Okay. All right. In the pipeline steps. If you want, I can show it to you maybe tomorrow.
Okay.
Okay.
I'll try it if I have any doubt.
That in case if you want me to do that, I'll do that in the next class also.
Okay.
All right. Anyone with any other questions? Okay, then people, let's meet tomorrow. Take care. Bye-bye. Bye, everyone.
Thank you.
Thank you. Bye-bye.